At this point, we've talked about the definition of convergence and divergence for general series. And today I'd like to look at a class of series known as geometric series. To start with, we're going to focus on the finite version. So anything that we can express of the form 1 plus r squared all the way up to r to the n minus 1, we can call a geometric sum. So we've seen this kind of pattern before in some of our earlier examples. For instance, if I had 1 plus 1/2 plus 1/2 squared, etc., all the way to 1/2 to the n minus 1. A key characteristic that we should notice here is that for a geometric sum, I should be able to obtain a term from the previous term by multiplying by some fixed ratio, which we can call r. So what I'd like to start out with is considering how I could come up with a formula to evaluate this sum of n terms. So using the notation we've used before, let's let s sub n equal 1 plus r squared all the way through r to the n minus 1. Notice that we've been using s sub n to represent the nth partial sum. When we extend our pattern here to an infinite sum, we can interpret this sum of n terms as the sum of the first n terms. So this will kind of coincide nicely with that notation. So what I'd like to do is try to come up with what we've called a closed form expression for s of n. So right now, the only way I have of writing that is either using sigma notation or the ellipses there. So I'd like to be able to come up with a nice formula for this. To begin with, let's assume that r is not equal to 1. And we'll come back in a moment and talk about what if r is equal to 1. So a few things that we can fill in. So if this is s sub n, if I were to ask you to find r times s sub n, you could do so by simply multiplying each of these terms by a power of r. There would still be n things added together. Everything just has an increased exponent. Then I could ask for what is Sn minus Rsn. Notice that I'm going to take the underlined expression and subtract my first bullet point. So I have to think about what terms are actually, in some sense, present there in this notation. And what I want to observe is that there are a lot of similar terms. So we can think about what would cancel. So there is an r and an r squared and an r squared. And the next term that would come after r squared is r cubed. And of course that would cancel with this one. Likewise, when I think about this r to the n minus 1, there would also be one just before r to the n in the last term, so that would cancel. What would not cancel is these two terms that I've circled. So this would actually simplify to simply 1 minus r sub n. So at this point, if our goal is to find a formula for s sub n, I could observe that what I have on the left-hand side is this here. I could factor out Sn to write this as Sn times the quantity 1 minus r is 1 minus r to the n. Consequently, dividing both sides by 1 minus r, I could say that S sub n is 1 minus r to the n divided by 1 minus r. So this is a nice formula because it involves very little. I don't have to use sigma notation. I don't have this plus dot dot dot. And importantly, we said that this holds if r is not equal to 1. We could see the problem here is that if r were equal to 1, we would have been dividing by 0. Now, if r is equal to 1, this sum is a little bit easier to handle. S sub n would simply be 1 plus 1 plus 1, etc. And there are n terms. So Sn would simply just equal the value n. So in the special case that r is not equal to 1, or excuse me, that r is equal to 1, we have a slightly different summation there. So now we can use this in order to talk about the infinite sum that follows this pattern. So in some sense, we've now come up with an expression for the nth partial sum for our infinite sum. So now consider, and I'll express this in sigma notation, the sum from 0 to infinity of r to the k. So in order to determine if this series converges, we need to look at the limit of its partial sums. Now, one thing to mention here that might be a little confusing is we've typically been expressing the partial sum, the nth partial sum, as the sum from 1 to n. Notice here that I'm essentially writing it as the sum from 0 to n minus 1. There are a couple things to think of. So this Sn, you could think of it as r to the k, summing from k equals 0 to n minus 1. And of course, you could also think of it as r to the k minus 1, summing from 1 to n. So the key feature to think of is that the nth partial sum really should just represent the sum of the first n terms. And as long as we focus on it that way, we don't have to stress too much about if we're starting at 0 or starting at 1. If you were to think about how many terms are being added there would be n of those. So I want to know what happens then to these expressions as I send n to infinity. So considering this, we have, again, two cases. So first of all, if r is not equal to 1, then the limit as n approaches infinity of s sub n is equivalent to saying, let's find the limit as n approaches infinity of 1 minus r to the n over 1 minus r. Importantly, this is the only thing in here that is dependent upon n. So when I'm thinking about this limit, that's what we're going to focus on. And so the value of r very much affects whether or not this gives me a finite limit. If r is between minus 1 and 1, then what's going to happen is we're going to raise that value to a higher and higher power, and consequently r to the n is going to shrink down to 0. So in that instance, we would get a finite number. If r is either less than minus 1 or larger than positive 1, you're going to not get a finite limit. In the case where r is greater than positive 1, r to the n would just grow without bound. If it were less than negative 1, it would grow, but also oscillate, so that limit wouldn't exist. So essentially, I'm going to be able to say that this will approach 1 over 1 minus r if r is between these two values. And just to round this out, we need to consider the other case, which was if r was equal to 1. And in that case, talking about the limit of the partial sums is the same thing as saying what's the limit as n approaches infinity of n. Because remember, we determined up here that if r were equal to 1, the nth partial sum was simply n. Well, this limit is infinity. So in this case, we can see that by definition, the resulting infinite sum would diverge. So we can put this all together, and we're going to be able to say that the geometric series, which can be expressed as the sum from k equals 0 to infinity of r to the k, converges to 1 over 1 minus r when r is between minus 1 and positive 1. And I can more concisely express that as saying when the absolute value of r is strictly less than 1. So this is what we can conclude from the previous work up here. And I'll add that we also have a really nice formula for the nth partial sum for a geometric series. So sometimes we might be interested in summing a finite version of our geometric series. And we can do that with these sums we found up here. The last thing I'd like to consider in this particular video is to generalize this. So I mentioned before that a geometric series need not start at 1, with first term 1, k equals 0. And we can actually generalize our formulas. And at the end here, I'll box kind of the general formulas, which would be good to know in general here. So my generalization is, in order to be geometric, I still should have this pattern where each term is a common multiple of the previous term. So a geometric sum need not have first term 1. So we'll now consider the geometric sum which is the sum from k equals a to n minus 1 of r to the k. So this would be r to the a plus 1, r to the n minus 1. So what I'm going to do is take advantage of what we saw above. So I'm going to be able to say that this sum is, like we said, it's r to the a plus r to the a plus 1 plus all the way through r to the n minus 1. I can factor out r to the a and multiply that by 1 plus r plus all the way to r to the n minus 1 minus a. So just factoring that out. What's significant here is this is now a geometric sum whose first term is 1. We already have a formula for the part in parentheses. If I were to look back at our derivation, we would get this same kind of denominator. And the only difference is that the exponent on r should reflect how many terms there are within parentheses. And so what we can consider here is, actually I'll write that up in a moment I'll start with the infinite sum first. So that's going to be a general formula. Notice that in the instance where a is 0, r to the a is 1, and we get exactly the formula that we saw earlier. So this just generalizes it so that it might not start at at k equals 0. To consider that, we could then look at the infinite sum, and we would be able to take the limit of our expression where we're sending the number of terms to infinity, and we'd be able to show that the sum from a to infinity of r to the k once again has that 1 minus r in the denominator, but the numerator is r to the a. So I'll finish this off by emphasizing these formulas that you should know. We've gone through the derivation here, and I'll just collect the most generalized versions. So one of these is the finite geometric sum. So if I have the sum from k equals a to n minus 1 of r to the k, we can express that as r to the a times 1 minus r to the n minus a over 1 minus r. And the infinite version, if I have the sum from k equals a to infinity of r to the k, that is r to the a over 1 minus r. So these are very important, and I just want to highlight a few things about this. So in terms of remembering these formulas, I find it easier to note, first of all, this number up here is always equal to the number of terms. So that makes it easier for me to remember what the exponent should be. then this multiplier here is always the first term of your sum. And that goes for down here as well. Always the first term. And I often see people mixing these up, but keep in mind that if I have the finite sum, that's the only instance in which I know how many terms I have to think about having an exponent there. Whereas the infinite sum, of course, we have infinitely many terms, but we still have to focus on what the first term of the series is. So we haven't done any examples yet, but in the next video, I'm strictly just going to focus on examples, and we're going to put these formulas to use.